Welcome to the third module of this DTrace training. This module is titled Multithreading and it has been split in two parts because it's quite a comprehensive topic, and this is part 1. The agenda for this training is as follows. I would like to show you some resources, references that may be of help while you develop your DTrace program. Then I'm going to talk about timestamps and thread IDs. This is followed by a very important concept in DTrace called thread local variables. And the bulk of this training is formed by more examples. I'm actually going to revisit some of the examples that were covered in Module 2. This is the Oracle Linux DTrace user guide. The link is given on this slide, and I can really encourage you to download your copy, its PDF file, and keep it very close when you do your DTrace program development. It's a very good source of reference. The trainings are recorded and they're posted on YouTube. You can find them on YouTube, but there's also a nice single point of reference that you can use, the Oracle Linux training station. When you go to the link given here and then click on Oracle Linux, you will find the section on DTrace, and that's where the trainings are collected. So that's a very easy way to reference those, especially since I will be referring to the examples covered in Module 2. This may come handy. Timestamps and thread IDs. They show you when events happen. That's really useful, and it also helps you to identify threads so you know who is doing what. The built-in timestamp variable is a nanosecond counter, so it's a very large number that's incremented from an arbitrary moment in the past. That means it gives you an absolute time. In practice, that's not really very useful because typically you want to take differences so that you can get relative timings. And that's what you will see me doing in the examples that are to follow. It's an unsigned 64-bit integer. The built-in TID variable is very useful because it gives the reference of the current thread. It gives you the ID of the current thread. That's the ID as assigned to a task by the Linux kernel. Here we refer to this as the thread ID. It's a good way to identify different threads. And that's quite a natural thing that you want to do when you have a multi-threaded environment. For example, you can identify who's doing what. You can differentiate according to the thread that you're looking at. It has the variable type ID_t. It's essentially an integer. And here's an example of the use of the timestamp and TID variables. I'm going to use a target program in this example that has the name mxv-pthreads. It implements a matrix vector computation. It's been written in C and multi-threaded with POSIX threads or pthreads. And here's an example of the usage. You execute the program, and in this case we give it 2000 rows and 1000 columns to work on, and we're going to use 4 threads. Here's the question that we're going to try to answer using DTrace. We know the target program uses the function pthread_create to create the threads. Can you show the thread ID that executes pthread create, and can you give us the time that's relative to the start of the begin probe? Well, let's see how that works out. Here's the begin probe, and I'm going to say this one more time in this module and then I'll just ignore it. I'd like to show complete programs, and the first 4 lines execute DTrace and tells DTrace that we're going to use a script. And at line 3, I'm going to silence the default output from DTrace. Again, I'm not going to say that again and again, but you will see that in all the D programs that I'm showing. Line 5 to 8 is the begin probe, but it actually only has one line at line 7. At line 7, we use that timestamp variable, and we assign it to a variable called ts_base, and that sets the base value of the timer. It's a global variable, so it's accessible anywhere in the D program, and that's exactly what we want. We're also using the PID provider to look at that function pthread_create. So we write a probe, in this case an entry probe for pthread_create. That is defined from lines 9 to 14. At line 11, we use that variable timestamp and we subtract ts_base from it. We convert to microseconds by dividing by 1000. Because these are nanosecond numbers, they're very, very large and they're generally not very meaningful. It's quite common to convert it. In this case, we convert it to microseconds by dividing by 1000. That happens in line 11. We store this value in a variable called t_start, and we make it a clause local variable, so it's specific to that to that clause that voids, if we would make it global, there could be interference with other probes firing with that same name. It's just a safe way of doing it. This is a variable that is local to that probe. And at lines 12 and 13, we print it. Note that we use the thread ID here at line 13. So we print the probe func, you've seen that before, then the thread ID and that time. And I would like to point out that in the remainder, I will convert all the times to microseconds. I just find that more convenient. There's another function that can do that. There's a normalize function that you can use to actually scale aggregations. There's a little bit of a side comment, but just in case you would like to do that, let's say you store timings in an aggregation. You can normalize to a certain number, and the normalize function is very convenient for that. Here I will not use that. I will just simply divide my numbers by 1000. And this is the output. We run the program as usual. You've seen it before. My program, my D program, is stored in a file called ts.d. I execute my mxv pthreads program, and I'm going to run it with the parameters that I've just shown. And recall, I'm using 4 threads. The 4 lines to follow, that's the output of our D program. And what we see is there are 4 threads created, as we would expect. But we also see that the thread ID is the same. So one thread is creating those other 4 threads, and this is the ID of the creator thread. And then we see the timestamps in microseconds, and we see that one by one these threads are created. So this is a sequential process. It's the first observation that we make. That's fine if you have a small number of threads, but if you want to create many threads, you probably want to have a more parallel version of creating threads. In any case, this is the kind of information that you very easily get with those 2 variables. I now want to talk about thread local variables, and that's a really important concept in DTrace. You absolutely need them. They're sort of indispensable. What's a thread local variable? The value of a thread local variable is preserved across the probes executed by the same thread. What does that mean? It's a variable that's accessible to that thread throughout its execution. You can call it a global variable, but it definitely has a very wide scope because the thread can access its thread local variables from wherever. And that's really very powerful and useful. So thread local variables are very important, and you will see them in many D programs. You declare them by using the keyword self. Self followed by the arrow, and then the name of the variable will declare that variable to be a thread local variable. And in this case, I assign the value 10 to it. When do you consider using a thread local variable? Well, if a thread needs its own unique storage, and a simple example is the following. You've just heard about the timestamp variable. Let's say you want to time how long the threads take to do a certain task. That means that each thread will have its own local copy of the timer, because presumably that's different for different threads. And a thread local variable is a very natural way to do that. You can also use a thread local variable to access the variable across probes and clauses. It's almost like a global variable, but again confined within that thread context, and it can be really useful. And even if you don't have a multi-threaded target, a single-threaded target, the concept of a thread local variable can be very useful. And I will show you examples of that. There's one thing to point out, and it's very important actually. The storage of a thread local variable is persistent. That means they will stay around until you release them. That means when you have a large application, you have lots of threads, you have a lot of storage, the storage requirements may increase, and that could actually make you run into memory limitations, for example. That's not a good situation. So it's very good DTrace coding practice to release the storage when you no longer need it. And you simply do that by assigning 0 to that variable. And in my example, I'd initialize that variable to 10. Let's say I want to release it. All I need to do is assign 0 to it, and then it will be gone from the memory system in a way. So you release that storage. Very important, and you will see me doing that in my examples. So by now we've seen 3 types of variables. There's the global variable. The global variable has an initial value of 0, but it's not thread safe. You've seen it, a global variable can be modified within clauses, in probes, but also by different threads. Very powerful concept, but you got to be really careful. Clause local is sort of the opposite. That's local to the clause, does not have an initial value, but it's thread safe. So that's like a local variable that you know of some other programming languages. Thread local sort of fits in between. It has an initial value of 0. That's quite convenient, and you'll see me leveraging that. But it is thread safe. Again, the thread local variable is only visible by the thread that owns it. We now need to talk a little bit about the scope and thread safety. We have scalar variables, for example, and associative arrays. They have a global scope, they're visible everywhere, they can be modified everywhere, and they're not thread safe. Especially with associative arrays, that's sometimes something to pay attention to. Aggregations have a global scope, they're visible everywhere, and they're thread safe. But that's kind of nice. In the remainder of this training, I'm going to look at examples, and I'm going to revisit the I/O and malloc examples from Module 2. I'm going to show you improved and expanded features. About these example programs. These are the same programs as we used in Module 2. The I/O program used there is a black box. All we know is it takes an input file as an argument. We don't know anything about it. And as was shown in Module 2, we could find out a lot about the I/O behavior of that application. There's also a memory allocation program. What it does, it allocates a memory block. It will use it, will initialize and use it, and then release that memory block again. The program would take several parameters, including the number of blocks, the minimum and the maximum size, and another option called -L. -L will allow you to introduce memory leaks, because that's the percentage of leaks that you want to have. Let's say you would do -L10. That says I want to have 10% of the memory leaks. In other words, those 10% of the allocations are not freed. And that will allow us to show some more features of DTrace. Here's the question. In the I/O example, in Module 2, we made a claim that fopen64 calls open. Can you actually show that? Before I show you the example, you'll see me using a function called copy in string. Why is that needed? Well, the DTrace command runs in the kernel. But in this case, we're going to look at functions in userland, and we get the pointer, in this case arg0, that points to memory in userland. So what we have a variable in userland, but we got to get it into the kernel, because that's where DTrace runs. And we need to use this copy in function to do that. That's nothing more or less than what it does, but it is important. Another feature I'd like to show is that the clauses for the return probes that you're going to see next are empty. And I do that to show you the default output. So far I've been silencing DTrace by putting it into quiet mode. Now I want to show you what happens if you don't do that, so you rely on the default output from DTrace. And here's my D program. It's very similar to what you've seen before in Module 2. I have my probes for the fopen and open, and all I do in those probes, that's at line 6, I print the file name. A file name that's stored in arg0, the first argument to the fopen and open calls. And here you see me using that copy function to copy the value the pointer points to from userland into the kernel. In that way I can do my printf, because again DTrace is running in the kernel. The second set of probes is at lines 8 and 9, and note that there's nothing in the clause. The clause is empty. That doesn't mean that you won't get output, because if you don't have the quiet mode, as I don't have here, I rely on the default, you will get information. As shown here, where I run the program as usual. You've seen it several times now. And what we see in that red line, we see the output of DTrace. DTrace tells me how many probes were matched. It tells me 4 probes were matched. How can we check that? The standard output shows the CPU ID, fine, but it also shows the probe ID, that's the second column. And what we see 4 unique probes here. They're reused below, but what we see, there are indeed 4 unique probes, so that matches with the output that we got from DTrace. And what we see, by default, we see that the function and the name are printed. So for example, we see fopen64, we see the entry probe. The line following, file name equals and then the name of the file, that's from our printf state. So it combines the output, which is very convenient. We can actually see what's happening there. And what we see, we have fopen64 entry and return, and within that we have the open call. We see the entry and return nested inside that. So this confirms that indeed that fopen64 calls open. We also have standalone usage of open 2 times, where we see the file name and we see the entry and return. And this proves the point that I was making in module 2, that fopen64 calls open. Another question. In the IO example from module 2, we were showing which files were opened and the file pointers and the descriptors, but we didn't connect them. The question is, can you connect the files and their pointers and descriptors? What was the issue in module 2? Well, we can get the file name, that's in arg0 in the entry probe. We can get the pointer or the descriptor, that's available in the return probe in arg1, but we cannot transfer the file name from the entry probe to the return probe. Well, how do we make that name available? You can use a global variable for that, but that's very risky. Let's say you have a multi-threaded environment and both will cause that probe to fire. Then you can get pretty disastrous results where one fire will eliminate the value from the other one. So that's not a good idea. In general, global variables are not good in this kind of scenario. A closed local variable is restricted to a certain probe. So you cannot transfer values across that using a closed local variable. Luckily, a thread local variable has the property that we exactly need here. And this is how we do that. In this first part of the DTrace program, I have my fopen and open entry probes. And what we see at line 7, I use a thread local variable. It starts with the keyword self and then the arrow. The name is at line 7 is fname_fopen, and I copy in the value of arg0. That's the file name. I do something similar at line 11 for the open probe, but note that I use a slightly different name. I'm using the name fname_open. And the reason for that will become clear shortly. But this creates 2 thread local variables. And the beauty now is that I can access them in the return probe. And now I can use that name in my return probe. Because it's a thread local variable, it's available to the thread executing that return probe. And the first usage is that I use it in a predicate to check whether the file name has been set. That's always good practice. Then I'm going to use that file name in an aggregation at line 16 as the second field in my key. And I'm going to use the pointer that I now get in the return as my third field in my key. And at line 16 in this aggregation, this is where you see that I can use both. I get the name from the entry and I get arg1, the pointer, from the return. So now I have indeed successfully linked those two together and I store that in an aggregation and I have my combined result. Always be careful to release the storage of your thread local variables, and that's what I'm doing at line 17 because I don't need it any longer. I got them coupled and we're done. And this is the open return probe. That's very, very similar to what we've just seen before. At line 20, I check whether the file name has been set. That's always good practice. Then at line 22, I have an aggregation. The name of the aggregation is slightly different because I need to differentiate when I print whether I should print a pointer or an integer. So I have 2 different aggregations. Other than that, it's very similar to what you've seen on the previous slide. And at line 23, I release that variable. And this also is a good moment to look at the reason why I introduced 2 different thread local variables, because at line 23, I wipe out essentially that thread local variable. Well, if I was using the same name in my fopen, that would be a problem, because when I get into the return of the fopen, recall that open is nested inside the fopen, that name is gone. You gotta have 2 different names, and not a big deal at all, and you release them as soon as you don't need them anymore. Printing the results is very straightforward. I usually have a printf statement to print a header and then a print a to print the results of the aggregation. And that's exactly what's happening here. So I get 2 tables for both aggregations. And this is the output. Run the program as usual. And what we get is we get the 2 tables. One is for the fopen64. Now it shows not only the file name, but also the file pointer, which is really nice. And then I have 3 invocations of open with the file names and the file descriptors. And now we know why the same file name appears in both fopen64 and open. In the last example, I'd like to look at the malloc and free example that I discussed in module 2. There I was showing how to get memory allocation characteristics like how many bytes were allocated and so forth. But there was one thing that was missing. I could not give a connection between the sizes and the pointers. So you malloc a certain size and you get a pointer, and it could not link those two together. Now the question is, can you do that? Can you associate the pointers with the sizes? Can you also show how long a certain size was in use and whether there was a memory leak or not? And again, we're going to make good use of thread local variables to tackle this. First of all, now we can make the size that we get in the entry probe, we can make it available in the return probe, similar as we just did for the I/O example. And with that, we can see whether a size pointer allocation pair has a call to free, because again, we can carry these values around and have them accessible in the free, for example. For the timings, I'm going to use the timestamp variable so we can measure the time between the return from the malloc and the return from the free. Before I show the D program, I want to talk a little bit about a choice that I made regarding print A. By default, print A sorts data according to the value. But that's not what I want in this case. So what I've done, I defined the aggregations such that the first column is either the size of the allocation or a timestamp. And then I'm going to set options to sort print A on the first column. That means my results will be sorted either according to the size of the allocation or the timing. And that's what I want to achieve. In this case, I'm using command line options to do that. You can also use pragmas in the D program. And to be honest, in this case, probably a pragma would be more convenient. But I want to show you how you can also do this at the command line. Here's the first part of my program. It's exactly the same as I showed a little while ago. I'm setting the base for the timings. And that's a global variable, so I can read it from any probe wherever I am. And that's exactly what I want. Then we'll have the malloc entry probe. I'm using the bit provider. And here what we do, I have a predicate to check whether the size is non-zero. Quite custom in DTrace programs, you're not interested in cases where the argument is 0. And here at line 12, I'm going to count the calls to malloc. And what I want to show you, so far I've been using keys that use standard functions, for example, like probe func. But you can have your own strings, for example. You can have your own index into your associative array or into your aggregation. Here I'm using an aggregation, call underscore count, and I'm using the string malloc as a key. And I'm simply counting how often this probe fires. And then what I'm going to do, at line 13, I'm introducing a thread local variable, size, so it's declared as self and then the arrow size. And I'm going to capture arg0, that's the size of the malloc. And in that way I store that value. In the return probe is now more complex. Here at line 16, I'm going to make sure that the size has been set. That should have been set in the entry probe. It's a good sort of defensive programming to check for that. Then at line 18 and 19, I'm using two associative arrays. These are not aggregations, these are associative arrays. There's no @ symbol at line 18 and 19. And at 18, I'm going to record a timestamp. I'm going to record the start time of the malloc. We're now finished, we're in the return part, so the malloc is about finished. And I want to know how long it took since the beginning, since the begin probe fired. So I'm taking the timestamp and I subtract ts_base that was set in the begin probe. Now remember that associative arrays are not thread safe, and here I want to make sure that I don't have any interference across threads. So at line 18 I make that variable, that element of the associative array, a thread local variable. And something similar happens at line 19, where I record the size. I have that, and I use arg1. In both cases I use arg1, that's the pointer, as the index. This is fairly complex. I use several features. I use the property of thread local variables, associative array, and I have my defined key to be the pointer. That's going to be the way I differentiate those elements. Then at line 21, I want to do some counting. I want to count each time the malloc is executed, and I use an aggregation is_allocated, and I have two fields in my key, the size and the pointer. That's what's happening here. And again, I now have access to that size that was set in the entry probe. And what I'm going to do, I'm going to add 1 to it, sum 1. Remember, aggregations are initialized to 0, so that's what I'm leveraging here. The first time it's called, it'll be 1, and a subsequent call would make it 2. Then at line 23, I release the storage, as we've done before. I no longer need it. The free, when we look at the entry probe, I have a little bit more complex check here. I'm going to have my predicate. I'm not only going to check that the argument to free is non-zero, but I also want to make sure that timer has started. And that's what I'm doing there. At line 28, I'm also interested in counting how often the free is being executed. And that's what I'm doing there. Again, using my self-defined key, in this case, the string free. And I store the pointer that I get out of arg0. And I do that in a thread local variable, so that I can use that in the next, the free return probe. That's a fairly long probe, so I split it in two parts. This is the first part. First of all, I check for that pointer to be set. Again, always good practice. Then I have at line 34 to 37, I have 4 different variables. And the names are quite long, and admittedly, it's because of me, I made them quite long, but I like this kind of coding practice because I'm using closed local variables to keep things local and give it some name. And instead of having those very long references, I have a shorter one. So at line 34, I'm going to compute the time. I'm taking the timestamp and I subtract the base time from it. So this records when we're sort of finished with the return and we're looking at the time since the begin probe executed. So that gives me that relative time. At line 35, I want to have my local copy of the size. So I'm grabbing the element from that associative array. Same for the timestamp that I had. Again, I could reference those elements on the right-hand side directly, but that would make things very, very long and harder to read, I think. At line 37, I can actually calculate the active time of that memory block, because I have the time, I know when I'm in the free return, and I know that's the second element that I subtract. That was when the malloc sort of started. At line 37, I can compute how long that block was in use, I should say, claimed by malloc. You don't know what happened with it, of course, but it's sort of what I call the active time. Then at line 39, I have my aggregation is underscore allocated. I use the size and the pointer as the elements of the key. But now I'm going to subtract 1 because I have a free. So when I do an allocation, I add 1. When I have a free, I subtract 1. And in that way, things should balance out or not. And this aggregation will actually show that to me. Before I show the second part of this probe, I would like to make an observation. I want to store statistics. I want to store that in a structure that I call stats for statistics. And I could use an associative array here. But the problem is there's no print A equivalent for associative arrays. The beauty of print A is that it will automatically print all the elements in the aggregation. So that's really nice. You don't have that for associative arrays. I would need to specify the keys when printing those values. Well, I come up with a little trick. I introduce an aggregation called add the stats. I can use print A to print it, and what I'm going to do, I'm not going to print the value because I don't care about it. So in sort of artificial way, I introduce an aggregation that gives me sort of the best of both worlds. And that is done in the second part of the free return probe. At line 40 and 41, I have this aggregation called stats, and the key consists of 4 fields. The timestamp, again normalized to microseconds. That was the start of the malloc. Then I have the size, I have the pointer, and I'm going to print the active time, again normalized to microseconds, and I have the count. But again, that count value is going to be ignored. I could put anything there. It just doesn't matter because I won't print it. Then I need to release the storage, as you've seen a couple of times before now. Just make sure that you release the pointer as last because you're going to reference that at lines 43 and 44. A lot of things have happened in this example, and I thought it may be useful to have a timeline of the events. We literally start in the begin probe by setting the base time for the timers. Then whenever the malloc entry probe fires, we capture the size. When we get to the return, we start the timer because that's sort of when the malloc is completed and we start the timer. We capture the pointer, we store it, and we store the size as well. And again, we using a thread local variable, we can transfer that value from the entry to the return. and we increment that counter where we count how many allocations and free we have. In the free entry probe, again, we capture the pointer and we decrement that alloc because that block has been released. In the return, we store the pointer, we store the size, we store the timestamp, and now we know the duration. We can compute and store that. In the blue boxes, it's shown how to compute those times. The time in the malloc is measured relative to the begin probe, and all we do is timestamp minus ts_base. For the duration, we are in the return. We take the timestamp and we subtract it from when we recorded that the malloc started. And that will give us again some sort of lifetime active time for that memory block. Here we print the results. It's very straightforward, very similar to what you've seen before. The only exception is at line 53, where when you pay attention to the format string, you see that I do not print the value of the stats because I don't care. Here's how we run the program. It's like what you've seen before. The one thing is those red colored options. What we're going to do is we're going to enable the sorting AggSort key equals 1, and we're going to tell DTrace to sort according to the first column AggSort key pos equals 0. That's what we do with those options here. The program is going to allocate 10 blocks, that's B10, and it's going to range in size from 1000 to 10,000. These are 64-bit integers, so the number of bytes allocated ranges from 8,000 to 80,000. With -L50, we're going to introduce 50% memory leaks, so 50% of the allocations are not free. Then what we see in the functions and the call count, we see that we have 6 calls to free and 11 to malloc. The first sort of observation is that there are 5 calls missing. That's by design, of course. That's what our test program does, but this confirms it. There are 5 calls to free missing. Also, we allocate 10 blocks, so why are there 6 calls to free and 11 to malloc? Well, this program needs an extra structure that's allocated, and that has a malloc free pair extra, so that's why we get 1 more. Then we have the output. The second block in the output, we see the start time in microseconds, the block size, the pointer, and the active time. And we can exactly see how long a certain block was active and the corresponding pointer. And the one thing sort of literally sticking out is that the first block was 80 bytes, was allocated at 163, and it had the by far longest active time, 423 microseconds. The other ones were allocated later and had a much shorter active time. And whether that's right or wrong, that's of course for the owner of the code to check, but it certainly points it out. And we also see that the pointer is reused 5 times. That's because we have the free, and the system clearly reuses things, which is a good thing. And also what we see here, of course, is that I have sorted according to the start time, so we see what happens sort of when. And although the times are relative to the begin probe, you can see the relative timings within that list to see when things happen. The second block of output, we count the leaks. And what we see, if there's a 0, it means the number of allocations and free were matched, so there's no leak. But we also see those 5 leaks here. We see a count of 1, so there's a free missing, and we see 5 pointers where that happens and 5 sizes. And this is a very easy way to identify memory leaks. Then wait a minute, there are leaks in this program, and now we have some information on the details of that. And this concludes the 3rd module in this DTrace training series. I hope that you found it useful. I hope this has given you inspiration to look at using thread local variables and also do your own timings if you like. And I'd like to wish you good luck in developing your DTrace programs. Thank you for taking the time to watch.